Okay, hello guys, welcome. We now go to tutorial number 2, thermodynamics of materials. So as usual, we start with problem number 1. The question for problem number 1 was calculate the weight composition of an argon helium gas mixture with a weight of 5 grams and a volume of 10 liters at a temperature of 25 degrees Celsius and at 1 atmosphere of pressure. So we are given a mixture of argon helium gas mixture, and the total weight is 5 grams, and the total volume is 10 liters. And we are also given the temperature and the pressure of that mixture. So this is the solution to this problem. So what are we given? So always when you are given temperature, you should convert it to Kelvin. So we are given 25 degrees Celsius, we get 273 to get 298 Kelvin. Then the gas constant, the R, can take two values of 0.082 liters atoms per degree mole, or can take 8.3144 joules per degree mole. So normally we use this 8.314 in units of joules per degree moles. Then we are also given mass of argon plus mass of helium, which is 5 grams. Then the total gas volume we are given is 10 liters. So the total pressure is the sum of the partial pressures of all the gas components, according to what is called the Dalton's law. But you should have just to know that the total pressure will be the sum of the partial pressures of all gas components, that is the helium and the argon components. They will produce the total pressure. So the total pressure is the pressure of argon gas plus pressure of helium, which were given in this case to be 1 atmosphere. But we know that the pressure of argon from the ideal gas law, because the argon and the helium can be treated as the ideal gases. So the partial pressure of argon is equals number of moles of argon times the gas constant times temperature over V. So the same with the helium, the partial pressure of helium is number of moles of helium times gas constant times temperature over V. So we can substitute the partial pressure of argon and the partial pressure of helium to get the total pressure. P total is equals number of moles of argon RT over V times number of moles of helium RT over V, where R is the gas constant, which I said is 3.14, is 8.314. Then the temperature is 298, the volume is 10 liters. So, but to get the number of moles of argon, we have to use the mass of argon divided by the molecular weight of argon, and for the number of moles of helium, we use the mass of helium divided by weight of helium. So we substitute the number of moles of argon, the number of moles of helium into our equation, and we get the total pressure is equals this expression, M of argon RT over M of molecular weight of argon times volume plus M of helium RT over molecular weight of helium volume. It should give us 1 atmosphere. So if we substitute the values into the equation, so we substitute the values into the equation according to, I told you about the gas constant. So in this case, we use 0.082 because we are dealing with the moles, and we substitute the 298 and the 10 liters, and the 40 is the molecular weight of argon, and the 4 is the molecular weight of helium. Then we substitute the volume and the temperatures are the same. So after doing that, we get this equation. One is equal to 0.06 molecular of argon plus 0.61 molecular of mass of helium. So we get equation number 1. Then after getting equation number 1, we also know we are given that mass of argon plus mass of helium is 5 grams. And we can now have equation number 2. These are two simultaneous equations which we can easily solve. And through solving them, we get the mass of argon is 3.74 grams. Then the mass of helium is 1.26 grams. So we can convert them to percentage. Percentage weight of argon is mass of argon over mass of argon times mass of plus mass of helium and 100 is 5%. And the weight of helium can be taken to the difference from 100, which is 175, which is 25% weight. So these are the ratios of the two, that is argon 75, helium 25% weight. Okay, so this was number 1. So we can now move on to our second problem, problem number 2. The thermal expansion coefficient, isobaric expansion coefficient, so isobaric is really the same pressure, is defined as alpha is equals to 1 over V partial T at constant pressure, because we are talking of isobaric conditions. And the isothermal compression coefficient is defined as this B is equals to minus 1 over V partial P at constant temperature. So this is the isothermal compression coefficient. So the following relation can be shown for some materials. So for some materials, we have this relation whereby we have Cp, a specific heat at constant pressure, minus specific heat at constant volume, is equals to alpha squared Vt over B, where alpha is the thermal expansion coefficient, B is the isothermal compression coefficient. So find Cp minus Cv for ideal gases. So we want to find Cp minus Cv for ideal gases. So we have to look for the equation for alpha, and we have to solve for beta, and we substitute into this equation to find the Cp minus Cv for ideal gases. So when dealing with one mole of an ideal gas, we know that PV is equals to RT, and we know that V is equals to RT over P. So we are looking for V because to solve for alpha, we should have to know partial V, partial T at constant pressure. So we want this V, and we get partial V, partial T at constant pressure for this V. So which is equals to 1 over V, and if we get partial V, partial T of this V, we get R over P. So it will be 1 over V times R over P, which is R over Vp. That is our alpha. Then the same with our beta is equals to minus 1 over V, partial P at constant temperature. And we have our expression for V. So partial V, partial P, we get, I think, minus RT over P squared. Then we multiply it by minus 1 over V. So we get this expression for beta, which is RT over V P squared. This is our beta. So this beta, we now substitute them, the alpha and beta, into our expression for Cp minus Cv is equals to alpha squared Vt over beta. So after we substitute, we get R over Vp squared Vt divided by RT over Vp squared. And if we simplify, we get R, the gas constant, showing that Cp minus Cv, we get our R. So this is for ideal gases, Cp minus Cv should be the gas constant R. Then let's go to the third and final question, problem number 3. So the following figure shows two base-static processes of 1 mole of a monoatomic ideal gas. So we're dealing with the 1 mole of monoatomic ideal gas, where Cv, specific heat capacity constant volume, is equal to 1.5 R, Cp is equal to 2.5 R, and Ta and Tb are isothermal curves. So let's look at the diagram. We have pressure, we have volume, and we have Ta and Tb. So isothermal means that they are occurring at the same temperature. So we have Ta, which is, and there's Tb, which is parallel to Ta at another. So Ta is at a higher temperature, Tb is at lower temperature. So this is the PV, which we have for that monoatomic ideal gas. So show that both the work and the heating process is A. That is, if you look process A from 1, you can say from, from 1 to 2 to 3 to 1, and in the heat from 1 to 2 to 3 to 1, and the heat and work from 4 to 5 to 6 to 4, show that they should be equal under this scenario. So we start with the process 1, 2, 3 to 1. So let's look at path number 1 to 2. So path, you can see from path number 1 to 2, it is a reversible isothermal expansion. We are at the same temperature Ta, and we are expanding. So it's a reversible isothermal expansion state. So the work done from path 1 to 2, so the system is expanding against the surrounding. So we put the so it will be minus integral from 1 to 2 P dV. It is expanding against the surrounding, so it's Px minus Px. But we know that, so it will be minus integral from 1 to 2 of P dV. But we know that Pv equals nRT, whereby T the Ta, isothermal temperature Ta. So we can get the expression for P, which is what? P is equals to nRT over V, and we can substitute it to get minus nRTA integral from V1 to V2 dV over V. And we can integrate integral for dV over V from V1 to V2 is equals ln of V2 over V1. So we get the expression which is minus nRTA ln of V2 over V1, which is the work done by the system when it expands from 1 to 2, from path 1 to 2. Then let's look at the heat absorbed or released from path 1 to 2. So we can use the first law of thermodynamics. So we say delta U is equal to Q plus W. So we know that Q is equal to delta U minus W at path 1, 2. So this is our expression. So work 1, 2 is the one which we have calculated minus RT ln of V2 over V1. So change internal energy during that isothermal process can be calculated from the definition of specific heat capacity constant volume. Delta U is equal to integral of NCV dt. So it should be realized that at this uh, because we are using an ideal gas, we can use the first law of thermodynamics for the internal energy using this expression, because the internal energy of an ideal gas is not affected by change in volume or change in pressure, but is also only affected by change in temperature. So, but you see that the change in temperature, because it is an isothermal process, the temperature is not changing. So the change in internal energy, when it expands, it will not change in its internal energy. So it will be equal to zero in this case. So get the expression for Q, which is nRT ln of V2 over V1. So, but you should have to realize that V2 over V1 should be is equals to TA over TB. V2 over V1 is equals to TA over TB. I will show why do we say that V2 over V1 is equals to TA over TB. So this is because V2 over V3 is equals to V2 over V1, which is equals to TA over TB. And I'll show in the next slide why do we get such a relationship. So let's go to the next slide. And we want to show that the relationship is valid. So let's look now at our diagram, path 1 to 2 at constant temperature. So from 1 to 2 at constant temperature, we know that the temperature is constant, and because it is an isothermal process, so when temperature is constant, the relation in which it holds is pressure is inversely proportional to V, as you can see from the plot of the curve at T. It will be an isothermal where P is inversely proportional to V, which is called the Boyle's law. I think we've done it in our lecture. So you can see that from this it means that P1 V1 is equal to P2 V2 as we go at different points. This relation it will be a constant P times V. So at point number 1, number 2, number 4, number 5, P1 is equal to P2 V2, which is P4 V4, which is P5 V5. The relation will continue to hold like that. So it means that from this relation, V2 over V1 is equal to P1 over P2. Then we can also look from part 2 to part 3. That is from 2 to 3, you can see that the pressure is constant. So that is an isobaric process, which occurs from 2 to 3. So when pressure is constant, the relation which holds is called the Charles law, which says that the volume is proportional to temperature. So you can see this like that the volume to change in proportional to temperature. So as we lower the temperature, the volume will also be lowering. We will also be reducing. So this is the Charles law. So it means that at point 2, V2 over T2 is equal to V3 over T3 according to this relationship. And we know that T2 is equal to TA and T3 is equal to TB. So V2 over TA is equal to V3 over TB. So V2 over V3 is equal to TA over TB. We have another relationship of this form. Then we can also consider path from 3 to 1 at constant volume. So from 3 to 1, we see that the volume is constant, but the pressure is changing, increasing. So pressure is proportional to temperature. So as we increase the pressure, the temperature, you can see that it increases from TA to TB. So P1 over T1 is equal to P3 over T3. This is the change for the constant volume. So P1 over P3 is equal to T1 over T3, which is TA over TB. So we have this third relationship. So we can see that P1 is equal to P3 TA over TB. And we can take this P1 and we substitute it into the Boyle's law. So we substitute into the Boyle's law and we get V2 over V1 is equal to P1 is equal to P1 over P2, which is, and we substitute now for P1, which is P3 TA over TB, and we'll get TA over TB because pressure at number 3 and pressure at number 2 is the same. So P3 and P2 are the same. It's an isobaric process, so we get TA over TB. So with this, we can now see that this is TA over TB, which is V2 over V1, but we also said V2 over V3 is equal to TA over TB. So it follows that V2 over V3 is equal to V2 over V1, which is TA over TB. So after going through, we can see that this relation holds, and that is why we said from the previous TA over TB. So, but let's forget, we're moving to part now from 2 to 3 to see the weight and the heat involved in that 2, 3, which is an isobaric process from 2 to 3. So, from 2 to 3, we first calculate the work done from 2 to 3. So, work done is equal to integral P dV. And we can pressure is constant in this case, so we can take it out of the integral. And from V2 to V1, after integrating, we get minus P2, V3 minus V2. But we know that from the relation of an ideal gas, V2 is equals nRT over P2, and V3 is equals nRT over P3. So, because at 2 we have TA and at 3 we have TB, so we have these two relationships. So, if we substitute now, we get working from 2, 3 because minus P2. If we substitute our V2 and V3, we get this expression, which is minus P2 nRTB over P3 minus nRTA over P2. So we solve it like this, but we know that at point 2 and 3, the pressure is the same. So we can further simplify it to be minus nR, because P2 and P3 they will cancel, minus nR in brackets TB minus TA. So this will be the work done from 2 to 3. Then let's also go to the heat flowing from 2 to 3. It will be changing internal energy from 2 to 3 minus work done in 2 to 3. So we know that change in general energy from 2 to 3 is caused integral from TA to TB, NCB. So which is equal to, we now substitute our value for our given CP. Our given CP, this one is equal to 3 over 2R. So we substitute, and our N, this is our N. Then after integrating, get TB minus TA. So we get Q 23 is equal to delta U23 minus W23, where this is our W23, which we substitute switch. So which is equals to we put our internal energy, calculate internal energy, and our work, which we just calculated before. And we simplify this expression and you get 5 over 2 NR in brackets TB minus TA. This is the heat flowing in part 2 to 3. So we should be able to know that we can use this expression delta U is equal to negative from TA to TB and C dt for an ideal gas because internal energy don't change with changes in volume or pressure. It is only affected by changes in temperature. So we can use this expression for an ideal gas to calculate the internal energy required in the first law of thermodynamics. So finally, let's go to part number 3 to 1, from 3 to 1. So here from 3 to 1, you can see that the volume is not changing. The volume is not changing. So the work done from 3 to 1 is equals to minus integral P dV, where we know that dV is constant. So since dV is constant, we know that dV is equal to 0. So the work done from 3 to 1 is equal to 0. Then we want to calculate the heat now in 3 to 1. That's what the heat exchange internal energy from 3 in 3 1 minus the work done in 3 1. So the change in internal energy in 3 1 is equal to integral from TB to TA NCV dt. So which is equals to 3 over 2 NR. We supply the CV, which is 3 over 2 R, which was given as 1.5 TB minus TA. So which is equal to 3 over 2 NR TB minus TA. So this is the heat which will flow. So we can now sum all the heat from 1 to 2, 2 to 3, and 3 to 1. We can also sum the work done in those processes. So for the heat, we get this part. We get this part for the heat. We can get the first part, the second part, and the third part, and we can also it can be simplified to be this NRT ln of TA over TB plus NRTB minus TA. Then we can also the work done from 1 to 2 to 3 to 1. It will be we sum all the components which we're getting 1 to 2 to 3 and 3 to 1, and we get these two components. So don't forget that our intention is to show that the work and the heat in the first cycle should be the same in process B. That is from 4 to 5 to 6 to 4. So for 1 to 2 to 3 to 1 is the heat and the work. There's only dependent on the temperatures of the different steps. So therefore, the heat in process B from 4 to 5 to 6 to 4, they will show the same dependence because we are only restricted between TA and TB. So they depend on the temperature between TA and TB. So if you try to follow process B, that's doing exactly what we were doing in process A, and you get the same heat, the same work, because we are using the same temperatures and we are using temperature TA and temperature TB, which are parallel. So you get the same result. So this is very short. This is tutorial number 2. So if you have any questions, but what I want to emphasize is the calculation of the internal image. You can use the data you use equals to the graph of NEC because internal image of an electric gas is not affected by the change in volume or change in volume in pressure. It is only rely on the change in temperature. if you still remember the definition of an internal gas or of an ideal gas. So that is why we use that equation. So thank you very much for listening. If you have any questions, you can start to send them, discuss. Bye bye.